a couple questions have come up in email. A couple people received grades that were in the low 70s, and I do not need you to say anything right now because I really want you to keep your grades confidential. A couple people received grades that were in the low 70s on the last course. If it's under 75, I just want you to keep an eye on your grades overall, because that course is not 100% done yet. Remember, I told you, we still have the lab portion of it to do. Okay, so there's still 20% of the grade that is not counted. And if you do all your labs right once you get back on campus, you're not going to have a problem. Okay, so if you were in one of those borderline categories, and I would say that would be from a 70 up to the 75, which is officially passing, I wouldn't be that worried about it right now. I wouldn't be panicking. I wouldn't be counting on when you're going to retake the course, because as long as you do your labs right, I think you will be fine. You also have a practical exam that will be averaged into your exam grade. So I'm hoping that resolves that issue a little bit in some of your minds. Overall, the grades for the final exams were not bad. I actually saw the first attempts and the second attempts, and things looked relatively good. I didn't see any major areas of where I was concerned about. I felt that the grades overall, the exams did come out good. So again, I think that's something that the majority of you should be very happy with. Even your first attempts, I think you guys did do very well on your first attempts, which I asked you to do closed book, and then the second attempts I said you could do open. This course builds on the last one. Okay, this is a series. So 417, which is the course you just completed, the classroom portion of it, is actually a prerequisite to 1418. Now, under normal classroom circumstances, if you did not pass the prerequisite course, you would not be in this course. However, again, we're giving a little leeway because of the fact you guys haven't done your shop yet, and it wouldn't be fair to hold you to that same standard. Again, because the shop grade is missing. We can't do anything with it. So, again, everybody is moving forward regardless of whether or not you officially failed the last course. Now, if you got below a 60% in the last course, you and I will have a discussion in the very near future. Okay, because I do have some concerns. But that's not to say that the outcome's going to be bad. It's just going to say I have some concerns and we need to talk about it. So again, if you're in the low 70s, under 75, I'm not worried about it. Your shop grade will take care of that. If you're below that point in the low 60s, we probably do need to have a conversation, but I'm not going to do that on a recorded call. That is a one-on-one situation. Does anybody have any questions for me as we wrap up the last course? Okay. One more thing we need to talk about real quick. You're going to see a new name on the course material a lot of times. We have hired a new instructor for York. As you know, one of your instructors retired, wanted to spend more time with his family. It was a loss to see him go, but we are welcoming Mr. Barry Smoker into the mix. He is not taking over this course, but he will be observing and working with me for the duration of this course. He's also been working pretty hard on the labs since we can have one or two people in the building. And him and Brad have been down there maintaining their social distancing with masks on and everything else, getting the labs put back together, getting those air conditioning system pipes, getting the trainers piped and rearranged, working on the boards and everything else, and they're starting to work on the oil furnaces as well to get that all up and ready for you guys. So please, again, please everybody realize Mr. Barry Smoker's on the line with us. As I said, he's going to be observing initially. He may be involved in some of the discussion posts, some of the grading of the assignments as we move forward. But if you have any questions, reach out, and I'll be happy to answer them. So, Okay, moving on to the actual course. Guys, this is pretty critical. I need everybody to have a very clear understanding of this. This course is an advanced course. It does move relatively fast. As always, I do encourage you guys to look at the syllabus. Okay, this is a 107-hour course. 47 hours of it won't be done until you're back on campus. 60 hours of it are considered our related instruction. That's our classroom instruction. We also have 26 and 3/4 hours of basic homework. Okay, now everything right now is sort of pushed together, but even though you're from home, even though you're working from home, and I give you 24-hour days to do your work, we still have to remember that there's about 5 hours of coursework every day for this course. Okay, now I do try to give you guys more time. I do try to work with you on, I know some of you are working rough schedules right now because of your employer has changed their schedules around. We make things available for a minimum of 24 hours, okay? Most of our daily assignments open at 12:01 a.m. and close at 11:59 p.m. Okay, watch your due dates. Okay, daily assignments, as some of you found out, I do not accept late work on. Any other work that's late loses 10 points a day. That's automatic. Okay, so watch your due dates. There's a couple places you can go for the due dates. You can always go look at the bottom of the syllabus. Okay, so if you go all the way down to the bottom of the syllabus, there's a course summary. Your due dates are there. If you're using the Canvas app, there's a tab for summary. When you go to the syllabus link, there's a tab for summary. Okay, watch your due dates. When you get back on campus, there's a dress code requirement. Okay, make sure you have reviewed that. They're not going to let you in the shop unless you follow the dress code requirements. Okay, that's an absolute. So there's a couple things on the syllabus you guys need to review. If you haven't done it, it's very much the same as the other syllabus, but just be aware it's there. That's all I need to say about that one. The book for this course, you're going to use primarily the Modern Refrigeration book. Math for HVAC is listed as a book. You guys have it. I know you have it. Okay, it's on your bookshelf. In one of the prior documents that were out there, Applied Math was still listed. It's not required for this course. It was the old math book, and for some reason it was still on a document. Any questions on the syllabus? Okay, moving on. Make sure you check my announcements every day. Okay, my announcements tell you important things in the course, okay? Tells you important due dates, tells you when our lectures are, tells you anything else I need you to know, okay? I put them out there on a daily basis. I can tell who reads them. Everything you do in the course is logged. Today, there is no assignment of the day. That starts tomorrow, okay? Because I can't very well ask you questions on stuff I haven't covered yet. So don't worry about an assignment for the day, but I do expect to see activity in the course. In other words, I can tell if you've read my assignment of the day. I can tell if you clicked on some of the videos. It's very important that any of the videos that are out there on the course overview, okay, when you go to home, there's a course overview. Okay, it's extremely important that the videos that you're watching on the course, that are on the course overview, you have watched, okay? We've put a video out there how to download, complete, and submit PDF assignments, and we've put a video out there on how to find due dates in the Canvas app. I need you to watch those. Then under today's module is we're going to be talking about pressure switches, condensers, and subcooling. Okay, when you scroll down to the bottom of this, there are videos down there. Okay, video lectures. There's one on simulator overview. I need you to watch that. Okay, and these others we're going to talk about, but they're here for your own good. Okay, if you miss my lecture, if you want to hear something again, please watch the videos. Okay, my lecture video will always be added on to the bottom of this one. Any questions? Okay, let's go ahead and start with the material for today. Okay, first of all, before I go too far, let's take a look at this diagram here. Okay, this is a refrigeration cycle. Yeah, it's a relatively old worksheet, but it still works the best. Okay, it still is very, very valuable to us in terms of a couple different places. Okay, first of all, what can somebody tell me about this diagram with compared to the other ones we've been using, other than the fact that it's not color? Come on, folks. What can you tell me about this diagram other than the ones we've already been
There's
using?
a lot more stuff.
There's a lot more stuff, but what about where the evaporator and the condenser is?
The positions are reversed.
The positions are
Yeah, they're backwards. Does it really matter how we draw it?
No, because the refrigeration cycle is a circle anyways.
Yeah.
Just depends on which way. Yeah.
Okay, so this is a worksheet you're going to see on and off, okay? Let's start with the bottom part of this. So basically what this worksheet is asking you is for each of these pressure points. You see TP1 is right there. TP2 is right there. TP3 is right there. TP4, those are all basic temperature pressure points. Different places where you can take temperatures and pressure, okay? So now, if I drew my lines on here, okay, where are my 2 points of pressure change in any refrigeration cycle? Where's my 2 points of pressure change?
Compressor and the median device.
Okay, so if I come across here and drew a line, okay, TP1 will be on which side of it, high or low pressure?
High side. The high side.
Yeah, TP1 is going to be on your high side. What about TP4?
On the low side.
on the lower side.
Oh, really? It's still on.
No, it's still on the high side, yeah.
Still on the high side because the metering device is my point of pressure change. What about TP5?
Low side.
Low side, that's correct. What about TP6?
Also the low side.
Okay, 7?
And the low side again.
Okay, so we have a very clear point of pressure change. Okay, now, what if we take a look at liquid or gas? Where are my 2 points of state change?
Condenser and evaporator.
Okay, so if I basically came across with a line, okay, and this is roughly because, you know, there's a period in here where it's really mixed, okay, above my line, is it liquid or gas?
Gas.
Okay, which means below my line, it's all liquid. Okay, so starting with TP1, okay, starting with TP1, is it a gas or is it a liquid?
Gas.
Okay. What type of gas?
High pressure, high temperature.
Say that again. I heard it had some background. What
High
else?
pressure, high temperature.
High pressure, high temperature. What about TP2? Careful.
Same. Well, is this where it starts to de-superheat?
Okay, TP2, if you look at the combination here, if you look at the little, and it's tough to see, but it's a little line through it, right?
So it's still vapor
So it's
then.
gas in a liquid, so we consider it saturated. Okay, it's starting to do its change of state. What about TP3?
It's liquid.
Yeah.
Yeah. It's right as we're coming out of the change of state, so we're liquid. What about TP4?
Also liquid.
Yeah, that's our liquid line as it goes into the metering device. What about TP5? Now be careful here. What do we consider that gas coming out of the metering device?
Flash gas.
Flash gas, which is really what? It's a low pressure what?
Vapor.
It hasn't boiled off yet. It's just in the process. So it's sort of a combination of flash gas and low pressure liquid. Okay, so we're going to consider it saturated. Okay. What about TP6?
Gas.
Yeah, I'm going to go with gas. It's right there on the borderline of the saturated, but I think they're trying to show it as a gas. Of course, it's not going to let me... Okay. What about TP7?
Gas.
Okay, it's a gas. Now, does anybody have a temperature pressure chart close by?
Yeah.
Okay, find your R22 column.
Okay.
Okay. Before you look totally at the temperature pressure charts, on my chart, what can you tell me about the pressures all the way from TP1 to TP4?
Under 100 psi.
Yeah, my pressures do not change between TP1 and TP4. So in other words, I can come in here, okay, I can come in here and I can write 100. Well, I'll have to move it after I write it because it decided to put it in the wrong place. But I can write 100 all the way through here, right?
Yes.
And again, it's got to move it around a little bit. There we go. Anybody see a problem with that? Okay, because my pressures do not change through the entire high side of the system. Now, if I'm being given a pressure at TP7 of 17, what's my pressures at TP5 and TP6?
About 43. 48.
My pressures, if I'm being given a pressure at TP7 of 17 psi's, what's my pressure at TP5 and TP6?
17.
83.
17. It's all on the same side of the valve, right?
Yeah.
Okay, because remember, my pressures do not change in any place but two places. So if I'm being given a pressure, okay, of 17 psi at point TP7, my pressures do not change at TP5 and TP6 most often. Okay,
I'm
so,
sorry, real quick. What does the TP abbreviation stand for?
just temperature pressure point.
I see.
It just could be a valve, could be a service valve connection or a point you can put your gauges on.
So there will never be a difference in temperature, say from TP5 to TP7.
Not.
And if there is, there has to be some sort of malfunction with the fan.
Wait a sec. There will not be a change in pressure unless the coil is extremely long. And we'll talk about that when we talk about evaporator coils.
I meant to say pressure, not temperature.
Yeah, most often, if there's any small change, it might be 1 or 2 psi, and it's only in extremely large coils. Okay, which we'll account for. But 1 or 2 psi doesn't do much on your gauges. But the pressures remain constant throughout the entire low side of the system. pressures remain constant through the high side of the system. Your one biggest difference is temperatures. Okay, so that's our next line here. Looking at your temperature pressure chart under the R22 column, and I'm trusting you, I don't have one in front of me. What is the temperature for 100 psi?
Oh my God, I don't know.
195.9.
No, that's the.
Say that again. I'm sorry. I barely hear you.
The pressure is 195.9. The temperature.
No,
So 196 base, 196. Does everybody agree? Who's looking?
No. What was the question again?
For a pressure of 100 psi, what's my temperature?
See, no, it's 60, right?
So you're going to come down the center.
60.
The temperatures are on the left side.
It's
Yeah,
61
yeah.
or 60.
I buy 60. Yeah, it's 60.
Okay. It's 60.
Yeah, 60.
Okay, now I'm going to make a correction on here because originally this was set up for R20 or R12, and we don't have R12 on our pressure charts. Okay, so do me a favor. Again, ignore that 90 right there. It doesn't work. Okay.
And this is
So,
R22, correct?
This is R22, yes. Okay. Now, at TP3, what should be my temperature?
Same thing.
Same thing. Remember, we're doing a change of state. We're not changing sensible or late. We can't measure the latent heat change. We can only measure temperatures. Now, column 4 is where we get into a little bit of a tricky situation, okay? And we're going to be talking about this today. That's why I really wanted to look at this chart a little bit, okay? We're going to be talking about subcooling today. Subcooling is the sensible heat change that happens following my change in state through the remaining, and I have a lot of background noise here, through the remaining portion of the condenser coil and the liquid line. It's a sensible heat change.
Can you say that one more time, please? There's a little out of
Yeah, I'm going to mute somebody, too. Okay, subcooling. Hang on a sec. Okay, hopefully that's better. Subcooling. It's the sensible heat change that happens following the change of state in the last pass of the condenser and the liquid line. The refrigerant changes from a gas to a vapor, a gas to a liquid. That's my change of state. It will continue to cool, and it will continue to give off heat because it's still warmer than the ambient air. That's the outside air. So all the way from TP3 on this chart to TP4, the refrigerant is going to continue to give off heat. That's sensible heat. I can measure it. So if I know my condensing temperature point, and if I know that the temperature of TP4, I can subtract the two and I get my subcooling. In this case, I'm being given a 12-degree subcooling, so my temperature at TP4 is 100 minus 12, which is what?
88.
88. Okay. Subcooling. The difference in
So where is the
temperature,
12 coming from?
That's just a given, okay? That was something we gave, but it's the difference in the condensing temperature and the temperature that I've taken of the line set. I put a clamp on thermometer at the line set right here before the metering device.
Wouldn't it be 60 minus 12?
No. 188 is 12, right?
No, I understand that. It's just that the temperature in TP2 and TP3 is 60 and the pressure is 100. So for doesn't the pressure?
Oh yeah, sorry about that. Yep, you caught me on that. So it's 60 minus 12. Sorry, you're right. My fault.
That's all.
Okay, so again, temperature of condensing temperature minus temperature of the liquid line going into the metering device or wherever I'm taking it. Normally I'd be taking it as it comes out of the condenser, but that's okay, is subcooling. Now, do these numbers make sense on this chart?
No, the TP4, the pressure, when you have temperature of 48, the pressure should change too, right?
No, that's the whole thing. The pressure does not change because the pressure is actually telling you what's happening in the condenser. It tells me what my point of saturation is. It's the exact temperature that the change of state is going on.
Can the pressure be changed from the compressor? Like, can you adjust the compressor to certain pressures?
Can't adjust the compressor, but I can add and remove refrigerant within a reason. Now, why don't these numbers make sense? Okay, other than the fact that, I mean, it's a very valid question that why didn't the pressure drop here? But pressure on the high side will never drop. Why don't these numbers make sense? Think about it. And it's okay to be wrong. Okay, I'm going to ask you this question again when we get done with today's lesson on condensers. Okay, think about this chart as we're going through the condensers. Very specifically, think about the 60-degree temperatures of my condensing temperature. So if I asked you what subcooling is, and again, I'm being sort of unfair here because I haven't gone over the lesson yet, but if I ask you what subcooling is, what is it?
A temperature of a liquid when it is cooled below its condensing temperature?
Exactly. Okay, believe it or not, it's a measurement of how full my condenser is in refrigerant, and it also tells us a lot about efficiency. Okay, so now let's talk a little bit about, now it's time to talk about condensers. Okay, now every system out there has a condenser. We've already talked about compressors. We know compressors a vapor pump. So let's talk a little bit about condensers. Okay. We have two types of condensers. We have water-cooled and we have air-cooled. Okay, now for residential air conditioning, which type do we see the most?
Air-cooled?
Yeah, we're not going to see that water-cooled that often unless you live in a McMansion up either in Old Town Philadelphia or up in the center of Boston or that area there. Okay, water-cooled is, you have some very large residents and old houses that we use a ton of water-cooled. We can also use water-cooled a lot of times in, if we have historic houses where we can't get ductwork and stuff like that through, we sometimes may use water-cooled systems. But the majority of everything we do is air-cooled in residential. Okay, air-cooled condensers are called forced draft condensers. All that means is we use fans and blowers to move air through the coil. We have fins that are connected to the condenser tube to provide more surface area for heat transfer. By the way, that is a final exam question. Why do we have fins on the condenser tubes? Okay, it's exactly so we can have more surface area for the heat transfer. The greater the surface area, the more efficient my heat transfer happens. So this is a basic residential condenser coil. Okay, this is a little short one, but you see we have the copper tubes in here, and then around those copper tubes, sort of mounted to them, we have fins. Okay, those fins just extend the surface area of that condenser. Okay, it's forced draft. We pull air through it. Inside the copper tubes, if you look closely at this PowerPoint, the fins are rough. They're not smooth on the inside. Again, we want to have we don't want a smooth surface because we want that refrigerant to spend as much time on all areas of this tube as possible so that there's much more surface area than just a smooth surface would have. You don't see this as a customer. You don't often see this as a service technician. But no, it's there. Those inside of those tubes are rough. So this is a basic example of an air-cooled condenser. We have hot gas in. We have cool liquid out. You have fins, okay? And 9 out of 10 times you're going to find air being pulled through the condenser coil. We rarely push air the other direction, but air is pulled towards the fan through the coil. Okay, now, condensers come with different number of rows, and when you get back on shop, one of your lab projects has you look at this. Okay, but because it's going to ask you how many passes or how many rows does the condenser have. Okay, basically you look at how many rows. So you have 1, 2, 3, 4. Okay, so this condenser has 4 rows of coils that are sandwiched together. You can sometimes find that out by looking at the manifold as well, which is at the beginning and end of condenser. So this is basically this condenser has 4 rows sandwiched across each other, and one of your labs actually has you look at that. Okay, you'll be given a piece of equipment and you'll be looking at the condensers. Now, what happens when this condenser starts building up dirt on the outside of it? What happens? You start building up dirt on the outside. What happens to the air that's coming through here?
The air is restricted.
Starts restricting the air. Can I exchange heat with the ambient area if I don't have enough air coming through?
No.
No. What's going to happen to your condensing temperatures?
They're going to rise.
They're going to rise.
They're going to rise. What's going to happen to your pressures?
It's going to stay the same.
No.
They're going to get higher as well.
Right?
If my temperature of my condensing point rises, what's going to happen to the temperature of my condensing point, or the pressures of my condensing point? Think back to the refrigeration cycle I showed you. They're going to get higher. So if I have a dirty condenser coil, my pressures are going to be higher or lower than normal?
Higher.
If my condenser fan fails, my pressures are going to be higher or lower than normal?
Higher.
If I have a very, very cold day outside, my pressures are going to be higher or lower than normal?
Lower.
Lower. See where I'm going with this? Your condenser plays a significant role in the operation of the system all the way. Okay, now, something very important that we don't mention, that I don't have written in this PowerPoint because we talk about it more when we do troubleshooting. If I start having dirt buildup between these condenser coils, these different passes or the rows of the condenser coil, you might not necessarily be able to see it from the outside. but you'll know it's there because of the pressures. Okay? It's very easy to have dirt buildup between these condenser coil passes. Okay, and then it just has to be cleaned, and that can become a big job. So when people cut their grass and blow the grass clippings at the condenser, okay, they're actually making their systems less efficient. Okay, something we haven't talked a lot about is when the pressures increase on that compressor, what happens to the compressor amperage? My pressures get higher on my computer.
It rises.
It rises. So if my compressor amperage goes up, if the load on my compressor goes up, if my system isn't cooling properly to start with and has to run longer, what happens to the customer's power bill?
Goes up.
It goes up. Okay? The condenser, believe it or not, is one of the most important parts of an efficient system. And cleanliness makes the biggest difference. Okay, another type of air-cooled condenser. This you see more with refrigeration and large roof installations. Okay, again, the point here is we're pulling air through the system. Okay, I'm pulling air in through the bottom. I'm sending it out on the top. The coil is under the fans. Okay? And all these little doors on the side here are access points. So A, you can get into the coils, but B, you can get to the fan wiring. Okay, this would be, you would see this on a large rooftop system. These are just a few condensers that you might see in a residential environment. Okay? This over here is the traditional split system, air handler on the inside, condenser on the outside.
I just have a quick question, Chris.
Yeah.
When like that rooftop unit you just showed, and some of these outdoor units, these commercial ones for homes, does rain and snow affect the system when it's falling directly? Usually
not. Where I normally see rain and snow affect this rain specifically, right under the condenser fan, and I don't know if you can see where I just circled. Right under the condenser fan, there's a splash guard. Okay, what that does, it prevents the rain from running down the shaft into the motor. Okay, if a technician replaces this motor and does not put a splash guard on, rain is going to run down that shaft and eventually rust out that motor. In terms of snow, if this system is running during the winter months, that condenser coil is warm. Like if it's on a refrigeration system, that condenser coil is warm. You're not going to have a lot of snow buildup. Okay, if the system is shut off during the winter months, okay, and again, if all the splash guards are in place, these systems are designed to be outside. You're usually in good shape. Okay? Does that help?
Yeah. So just rain or snow getting on the condenser itself isn't going to change the temperature or the pressure in the system.
Well, it will because it's colder. Okay? If I hose this down with water, if I hose this coil down with water, it's going to reject the heat much more easily than just hot air. Okay, so if I have a cool day, my pressures are going to run lower. If I have snow sitting on it, or if I'm running it on a below 32-degree day, my pressures are lower. We're going to talk about how to control that. I think we talk about that either in our pressure switch or we have another lesson on fan cycling. But we do have to talk about how these units run on colder days.
Oh, thank you very much for answering my question.
Okay. Again, it's more the temperature I'm worried about. It's not so much the rain or the snow. It's more the temperature. Okay, residential condenser sitting outside, light commercial, might be outside a doctor's office or whatever. I know somebody in this class has units that look like this, might not have two sitting on top of each other, but these are the ductless split varieties. Okay, I know somebody has it because we talked about it in our design class last term. So these are the ductless split. What is the big difference between these two units? Okay, let's not even talk about the inside. Does anybody remember what I said? What's the difference about these two electronically? There's a pretty big difference between the two. The residential, these systems over here, the traditional split system, most often uses contactors, AC fans, AC compressor, okay, uses traditional components. Yes, they're starting to have some pretty integrated circuit boards in it. Yes, we do have some ECM motors showing up and so on and so forth. The Fujitsu, the ductless splits, especially those manufactured and sold from a foreign market, all have direct current controls. Let me repeat that again. The Fujitsus, the Mitsubishis, some of the Daikin units, all have direct current controls. Okay, you need to be very careful on this because you can reach into this with your AC meter, you can put your voltmeter on it, and you can think to yourself, oh, the system's turned off, I don't have any power to it. But the reality is you are going to get one hell of a shock if you put your fingers in it without checking for direct current. I've heard of techs being hospitalized over this. Be very careful when you reach into these ductless splits. They have direct current controls. Okay, and their motors are direct current as well.
What about the heat pumps?
The heat pump the heat pump that looks more to my left side or more to my right side?
Left side.
They have primarily it's still AC controls, okay, and your regular meter will find the voltages for you. Yes, they have circuit boards in them, but primarily it's AC controls.
I'm curious on that mini split type system. What kind of DC voltage are we talking about, and where is it obtained from through those?
Okay, there's a rectifier as the voltage comes in. Okay,
is that on the outside unit, or
it's in the outside unit because everything is fed normally from the outside unit. Okay, that's the other thing that's different. A lot of times your on-the-wall units are fed from the outside units. Okay, and there's a rectifier that changes your 240 volt incoming voltage, AC voltage, to DC current.
And do you know what the voltage DC is?
Depends on where you are looking at it. You have a circuit board in there, okay?
Yeah, the motor as well, right?
Well, yeah. I mean, you have if you're looking at the circuit board, you might have control voltage, which might be plus or minus 5 volts, or could be based on amperage.
Yeah, so then if it did have like a DC motor, that's where that danger would be of not noticing right away.
Oh yeah, if you have a DC compressor in here, which a lot of them do, okay, or DC fans, you might have 200 volts on that compressor, and you might not notice it. So it's very important to always use your meter and check so you don't get zapped. Make sense?
Yeah, I think that answers my question.
Okay. Air-cooled condensers, normal temperature difference between the condensing point of the refrigerant and the ambient air is 20 to 30 degrees. Let me repeat that. It's an important number. The normal temperature difference between the condensing point of the refrigerant and the ambient air is 20 to 30 degrees. So if my refrigerant condensing temperature is 100 degrees, that means my outdoor air temperature is could be any place from 70 to 80 degrees. Let me say that again. The normal temperature difference between the condensing point of the refrigerant and the ambient air is 20 to 30 degrees. That means if my condensing temperature is 100 degrees, my outside air temperature could be between 30 and 80 degrees. Now, that is what I call a magic number. Different manufacturers could give you slightly different specs. Okay? So just be aware of that. Now, in refrigeration, some of you might have had refrigeration last term. Okay? The number's slightly higher. You'd see about 35 degrees. But in air conditioning, we're running about 20 to 30 degrees condensing temperature difference. Does anybody have a question on this? This is a very important troubleshooting point.
So, if it's, say, 80 degrees, your running temperature,
which running temperature? The ambient air temperature or the refrigeration temperature?
The refrigeration temperature.
Okay.
So that would mean that the ambient temperature, if the refrigeration temperature is 80, the cooling temperature is 80, then the ambient could be 60 or 70.
How about 60?
60 or 50.
60 or someplace between 60 and 50, yeah.
Okay.
Think back to the chart I just gave you. Those numbers don't exactly make sense because of the refrigerant differences, okay?
Yeah.
The condensing point of the refrigerant is found by converting the pressure in the condenser to a temperature. Okay, we've already gone over this. You're going to use your TP charts or the magic app on your cell phones like most of us use these days, okay? I don't normally carry paper TP charts anymore. Commercial air-cooled condensers. Okay? Big units. These are air-cooled condensers. Okay? Big fans on the top. Okay?
It's cooling
this
tower.
is one of these situations I take and drop the apprentice off on the roof with a hose and a bucket of soap. Okay? And let them spend the day up there.
I used to work on these.
You used to work on these?
Yeah, I used to take the fill out, refill them, build the fans back up, redo the whole insides.
Well, these are not, are you talking about cooling towers? These are not cooling towers.
Oh, they look like cooling towers.
Yeah, if you look, there's no sump in here. Remember the little pan that goes around the bottom of the cooling towers to catch the water? There's no water in these. This is just air cooled.
Oh, okay.
Okay, we're going to get to cooling towers. Okay, but these are all air cooled. Okay, notice the vibration abating legs and feet. Why do I have to have these on these things? Anybody?
You say right there, vibration.
Yeah, but what would happen if I didn't have vibration abating legs and feet on these things?
It'd go through the roof.
The airflow couldn't come up?
Oh, no. It would actually, you'd still have it on a stand, so I'd be okay airflow, but what would happen is the vibration of these units would actually rattle the entire building. Okay, these things vibrate no matter what you do with them. There's some vibration there. Sometimes it magnifies through roof structures and wall structures. So if you start getting service complaints about people complaining about that the building is noisy and stuff like that, and if you walk into the building and hear a humming noise that gets louder as you go up in the building, it's because one of these vibration abating legs or feet has gone bad. Okay, the units are sort of sitting on springs here. Now, are these units operational? The way you see them in the picture, are they operational? Anybody?
Look like it's, I'm gonna say no.
No,
Why?
those are the switches.
Looking at the switches, like they're down, yeah.
Okay, that's what I wanted you to notice, yeah. Okay, small stuff like that. So if you walk up on a roof and these are turned off and the problem is and you have a problem and the call is no cooling, okay, you need to find out why those switches were turned off. Hopefully there's a lockout tag on them. If they're just turned off, someone's causing trouble. Okay, subcooling takes place in the last few passes of the condenser. To measure subcooling, use the condensing point temperature and subtract the temperature of the refrigerant leaving the condenser. The temperature of the refrigerant is found by placing a clamp-on thermometer on the liquid line at the condenser outlet. Okay, so where the line set comes out of the condenser, you put a clamp-on thermometer on the liquid line. You guys have all seen my little gauges that I've shown you a couple times in pictures. That's what the clamp-on is there for. It's measuring the temperature of the refrigerant in the liquid line at the condenser outlet. Okay? So basically what we're doing is I'm taking my temperature right there. Usually at the condenser outlet there's a gauge connection and there's enough of a flat liquid line where you can take the temperature of the liquid coming out of my condenser. Now this is 134A. Okay, now we have a little bit of a problem on this condenser. Anybody see it? Anybody see a problem with this system?
The temperature? Is it the temperature? It stays the same?
No.
No?
No, well, the temperature might have something to do with it, but there's a problem in this diagram.
It's 184 psi, leaving the compressor, and it's 171 psi going into the metering device.
Yeah, that's a problem. There's an error in the book. Those should be relatively the same. I talked to the authors about this, and they were like, well, it might be a really long condenser, has a lot of restrictions. Okay, one of the best excuses I've heard in a long time. But what I want you to get at is that if my condensing temperature, okay, is 125 degrees, because that's what this is showing you. My condensing temperature is 125 degrees. Okay, if I come out of here at 110 degrees, okay, what should my subcooling be?
15 degrees.
You see the other problem in the book?
Oh, it says 10.
Okay, there's a lot of missing numbers in this. So again, my subcooling, condensing temperature, okay, minus line set temperature. Don't trust everything you read in a textbook. Okay? Questions on what subcooling is? Okay, water-cooled condensers. We have three types. These are primarily in commercial. You have tube within a tube. You have a shell and tube, and you have a shell and coil. Okay, I forget who said they used to work on the cooling towers. I didn't see who was talking, and I apologize. But you've probably seen some of these, if not all of them. Okay, tube within a tube. The outer tube carries the refrigerant, and I'll show you a picture of this in a minute. The inner tube carries the water. Okay, the inner tube often has fins spiraled around it to add surface area. This is a picture of it, okay? Tube within a tube. It's basically a double-walled tube. Inner tube carries the water. Outer tube carries the refrigerant. Please notice they are going in opposite directions. The refrigerant inlet is the hot refrigerant coming from the compressor. The water inlet is my cold water coming back from my cooling tower or coming from wherever my water source is. They are running in opposite directions. That's extremely important. Okay? So again, tube within a tube. Now let me ask you a question. Can you take a brush through this and clean it?
I'll say no.
No.
Yeah, no, that's the correct answer. That's the one problem, tube within a tube. They're very difficult to clean. They're not used on extremely large systems. They're used more often on smaller systems. And honestly, you're going to see these things more often on the refrigeration side than the air conditioning side. Okay, but this is a tube within a tube. You can use chemicals to clean it. But again, they don't last forever. Here's another example
that's high
of it.
pressure.
What is that?
So that line's high pressure too, isn't it?
Which one? Which one? The refrigerant side or the water side?
Well, since they're together, the refrigerant would surely be under pressure. It's on the high side.
Yeah, refrigerant is going to be under whatever you're condensing, whatever temperature here where my condensing is going on in the center here, that's going to dictate my refrigerant pressure. Water pressure is whatever the pressure is of the water inlet, and we sometimes adjust that to maintain refrigerant pressure. We adjust.
So the water tube is pretty much just a jacket. Is that like a two-piece that's soldered together, like two halves that are you sandwich together and soldered?
Not really, okay? If I take a big piece of copper tubing, let's say a 3/4 inch piece of copper tubing, okay? And then I feed another piece of copper tubing through it that might be a 5/8. Okay, and then I make a coil out of it, both tubings together. That's how these things are basically designed.
I see.
Hopefully I described that in a way you can picture it.
Yeah, no, I can, because I was picturing somebody trying to ram a line through a pre-bent piece of copper. And
no. This is something that I think a couple of the shops have on their refrigeration systems, because about 10 years ago, I had actually everyone do this as a student project where we actually took a roll of copper, you laid out the copper on the floor of the shop, straightened it out so it was a straight row, and then we fed a 1/4 inch piece of copper through it, and we made our own heat recovery coils. These are great for heat recovery because these water outlets can be used to feed a hot water heater.
But doing that, just for on a side note, I want to make sure if you were to bend that, to make your own, the refrigerant line would have to be longer than the water line.
Absolutely. Yeah, absolutely. And you have to be very careful that you don't kink anything.
Yeah, that would be a problem.
Yeah, here's a picture of one as it would sit in a unit. Okay, water in, refrigerant out. Okay, and again, it's normally in opposite directions of flow, counterflow. Okay, this is actually in what we call a geothermal unit. Okay, we'll talk more about those later in this course. This is in a geothermal heat pump. Okay, here's my compressor, and here is my condenser coil. And because this is a heat pump, there's a device in here called a reversing valve. Okay, and again, we're going to talk more about those. I don't want to confuse the issue right now, but they're the one place in residential systems where you're going to see the tube-in-tube condenser coils. Okay, geothermal heat pumps. Okay. If you look at the end side of it, you have the refrigerant in the center tube, or around the outside, the water runs in the center. Okay, there's little baffles sometimes that the manufacturers put into the tube so that inner tube might not be smooth, and that's to give more surface area. That doesn't have to be there. It works great without those. Okay, by varying the rate of the water flow, I can change my condensing temperatures. If I slow the water down, it's not going to reject as much heat. My condensing temperatures are going to go up. If I speed the water up, I'm going to carry away more heat. My condensing temperatures will fall. So speed of the water going through a system compared with the speed of the refrigerant makes a big difference in condensing temperatures. Shell and tube condensers. Okay, basically it's a long refrigerant cylinder filled with straight copper tubes filled with cooling water. The water circulates through the tubes, condensing the hot refrigerant vapor into liquid in the cylinder. Okay, straight copper tubes. There's a water inlet, there's a water outlet. There's a refrigerant outlet that's at the bottom, and there's a refrigerant inlet that's at the top. Again, let me say that again. Refrigerant outlet at the bottom. Refrigerant inlet at the top. This works on gravity. As the refrigerant condenses, the liquid goes to the bottom and gets sent out of the refrigerant outlet. When you clean these things, okay, you basically are pulling the cap off the end of it in order to clean it. Okay? You, of course, recover all the refrigerant, but to clean these things, we pull the cap off of here. And then you can send brushes through these. Nasty job. Okay? The shell and tube condenser is compact. It needs no fins. It combines the condenser and the receiver, which we haven't quite talked about, into one unit. It uses numerous straight tubes inside the receiver with a water manifold on both ends. When the manifolds are removed, the water tubes can be cleaned to deposits. Okay? Both the tube and shell and tube condensers can be cleaned by forcing a special brush through the water tubes or by using a chemical. Now, the tube, the brush doesn't really work that well. Okay, you really can't clean those, but the shell and tube you can clean. The cylinder body is made of steel. The shell and tube condensers are sometimes called shell and pipe condensers. So sometimes on state exams you will see the term shell and pipe instead of shell and tube. There's one more condenser type we have to be worried about. Shell and coil. The condenser consists of a coil of copper tubing that's wound around the inside of a metal refrigerant shell. It serves as both a condenser and a liquid receiver. All a receiver is a storage tank. Let's not overanalyze what a receiver is. It's a storage tank. It holds liquid refrigerant. So again, we have cooling water that comes in on the bottom, okay, works its way through a set of coils and leaves on the top. Okay, coming out of the compressor, we have our discharge line that comes in the top. Again, counterflow. And we pull liquid refrigerant out the bottom. Do I ever get vapor refrigerant out of this system at the bottom going to the metering device? Do I ever get...
No.
Why?
Because it's already cooled to the point that it's condensed, like into a liquid.
Yeah, the only time it ever happens is if for some reason I A, don't have enough refrigerant in the system, or B, I have a real condensing problem where I don't have cold water.
Or there's no water.
Or there's no water, yeah. Okay, so there's a problem if I'm ever getting vapor refrigerant out the bottom. Okay.
Just out of curiosity, do these water cooling systems, do they ever contaminate, like cause contamination to the coolant lines where water gets into those somehow and then they burn out the compressors?
Yeah, what would happen if I had a leak suddenly in the center here of one of these lines? Little pinhole leak.
Water would get into the line?
Water would get in with the refrigerant, yeah. That's a big problem because moisture in a refrigerant, okay, actually causes acid. So that will eventually burn out a compressor. But what's the bigger problem? Okay, think about my water pressures. Normally these water pressures are under 60 psi. Okay, I rarely go that much over 60 psi. My refrigerant in this system, with the exception of low pressure systems, which we haven't talked about yet, my refrigerant in this system is upwards of over 100 psi, 120, 180, and if it's 410A, we could be looking at a pressures up close to 400 psi.
It's going to start pressurizing the water system.
Yeah. Normally, the only time where it will leak out through the water side, but when the system's shut down, the pressures are more normally equal. But yeah, to answer your question, yeah, I can get holes in here. Okay, pipes will eventually disintegrate. Is water free of minerals? Is water free of acid sometimes? How clean is the water coming out of your tap?
I don't drink it.
Well, yeah. Okay, there's problems. Different parts of the country have different contaminants in their water. Okay, I couldn't have a system like that down here. I'm on a well. My water's extremely hard, and there's something about water in this area that will eventually corrode out copper. Okay, so there's a real issue with water in some areas. So water in these systems is 9 out of 10 times treated pretty heavily. pH is controlled.
So why couldn't they use like antifreeze or something in lieu of water?
We do. In recycled systems, we do.
Okay.
Okay. Yeah, we do. Okay. The shell and coil, again, smaller commercial units, that's the one that I just showed you. They're less likely to manufacture. However, they cannot be cleaned mechanically. They must be cleaned chemically. Those tubes are too tight of a turn to get any brushes through. Water regulating valves are used with water-cooled condensers to adjust the amount of water that comes through the condenser to maintain condensing pressure. There's a type of system that has to have water regulating valves. They're called open loop systems. They use city water. In other words, they use fresh water to send through the condenser, okay, to carry away that heat, and then they dump it or use it for other domestic purposes like hot water heaters and stuff. They're called open loop systems. We use fresh water and we do something else with the water. We don't recirculate it. This is a water regulating valve. Okay? Notice what it has on it. Can anybody see it?
A arrow.
Yeah, which way does the water flow? Always with the direction of the arrow. Don't put these things in backwards. They don't work. Okay, and I know that from experience. I messed that one up once. Okay, so your water line comes through here. Okay, this is a little copper line that runs down to one of the pressure ports on the high side of the system. Okay, there's bellows in the valve that's connected to high pressure access port. As the refrigerant pressure increases, it pushes on the bellow and forces the valve open. That allows more water to flow through the condenser. Okay, as the pressure increases, we allow more water to flow through the condenser. We're controlling our condenser temperature. Okay, so this is basically how it is.
The majority of the water going through that doesn't actually go in the system?
That's correct. It just circulates in the tubes. Here's my water regulating valve. So the water allows the fresh water from a city water supply or from a well to come through the tubes. The tube circulates through the center of my condenser, doing heat exchange with the refrigerant, and the water comes out of it. Make sense? And then if the climate is colder, okay, we slow that water flow down because our pressures don't need to be as high. Or we don't have as much load on the system. Questions? Anybody? Water regulating valve. What's it designed to control? What's its end goal? What are we doing?
Well, actually, I do have a question. It's about ice causing damage to the system if the system was to go offline or something with water in it in a cold climate.
Yeah, I could bust those tubes.
Yeah.
That's why a lot of times, that's why these things are normally installed inside. Yeah, you don't normally see these installed outside.
Are they more of a southern used thing, or do you find them all over the country?
You find them all over the country, okay, and you find, I got to find those pictures I have of the big chillers. I have some pictures that I took in New Orleans of a big chiller that I had to go take a look at, as well as some down here in Florida. You find them all over the country. They're used on big commercial chillers most often. Okay, and they're normally installed inside a mechanical room. We don't install these on the roofs. Now, there's one thing to realize, though, that the intake of city water, in other words, the open loop systems, we do not see that often anymore. Does anybody know why?
Probably because of all the chemicals they treat the water with.
Yeah, that's part of it, but isn't it a waste of water to just be using water and then dumping it?
Yeah.
Water's expensive in a lot of parts of the country. I mean, seriously expensive. The water meters and everything, they're very expensive. So we really don't use open loop systems. We don't install them that much anymore. Are they still out there? Yes. But do we install them that often, other than on like ice machines or something like that, in refrigeration? No, we don't install these anymore because, again, it's very, very wasteful. So more and more what we're using is what we call closed loop systems. In other words, it recirculates the water. And then I can put antifreeze and stuff in the water. So I can solve this whole problem. In water regulating valves, as the head pressure decreases, the spring on the bellows decrease and allows a spring to push the valve closed. The valve modulates and it maintains the correct head pressure and reduces water consumption, but there's something very else important in here. When I'm maintaining head pressure, am I maintaining, which is the condensing temperature, okay, is basically there's a temperature-pressure relationship. So if I'm maintaining 100 psi, okay, and if that equals 80 degrees on my temperature-pressure chart, by maintaining that 100 psi, I'm maintaining that 80 degrees. So again, my whole goal is I want to maintain the correct condensing temperature. When the compressor stops, the head pressure drops and the water regulating valve will close. Okay, again, try to prevent waste of the street or well water. When the compressor shuts down, system is off. The head pressure drops and the regulating valve closes. Now, this is what we see more often for what you're going to see more often. You're going to see water towers and cooling towers. Okay, this is used in all parts of the country. Okay, the other way to cool water, okay, is by use of a water tower or cooling tower. Okay, basically what we do is we blow air across the water, okay, and we cool it by evaporation. Okay, cools water in the water-cooled condensers. I forget who said that they were working on this, cleaning them as a job.
I have, yeah, me.
Okay, this is more probably what you were seeing. Okay, in one form or another. Okay, the water used by the condenser is stored in the tower and pumped to the condenser when the compressor runs. Water returns to the top of the tower after absorbing heat from the refrigerant in the condenser. Okay, so in other words, Okay, what we're using is this is just one variety, okay? We have a fan down here and we have a pump, okay? The fan pulls air in and blows it up the top. We use a spray pump that circulates the water and drops it down across the condensing coil. That's one version of this. So the water's circulating in here, and the evaporation, okay, of the water as it hits here, because you know when you evaporate water, it takes the heat with it. It's a change of state. So we drop the water across it with air, we evaporate the water, and we leave a cooler spot than we started from. That's how one type of water-cooled system runs. Now, there's many types of this. Okay, another one, okay, basically, again, this is just a picture of this cooling tower here, okay. We have our evaporator here, and in this case, we take water and we circulate it into the building, into a big condenser barrel. This might be the tube and tube, or well, more likely tube and shell. This is what you're going to see most often. So do you have any questions on this diagram? This is by far the most often setup you're going to see.
So the condenser is down underneath the...
yeah, it might be in a mechanical room in the basement. The condenser is this big barrel.
Yep. And that sits underneath the compressor in this diagram. The compressor is on top.
Yeah, this is what's called a big centrifugal compressor. Yeah. The compressor's mounted on top of it, barrel's right there. Okay, and then all I have going to the outside is water.
Is there any heat exchange between the compressor and the condenser?
Yeah, remember, anytime I compress things, it gets hotter. So the condenser actually is what helps cool the compressor because it provides it cools down that refrigerant and gets to the, remember I told you when we talked about compressors that the refrigerant is what cools the compressor.
Yeah, I was just wondering if there might have been any more, just because the compressor is in direct contact with the condenser, and the heat from the compressor. You're
going to find that when you work on these are such heavy metal. I mean, this is tons of unit here. Okay. You're going to find that, yeah, you can feel some heat exchange, but it's not bad.
Mm-hmm.
Because these actually, if you look very closely, there's a leg there. It's hard to see on this diagram, but there's legs there. This is set up so that the compressor doesn't overheat, if that's what you're looking at.
I'd hate to have to replace that unit.
It takes cranes and usually tearing down walls. Okay, the heated water falls through the tower, over baffles, cooling through evaporation, it gets to the bottom. The cooled water collects in the sump, which is the bottom of the tower, and gets pumped back to the condenser. Okay, so again, we have our heat-laden water coming out of the condenser. We spray it in the top, it falls down through baffles, it flows to a pump. Okay, back to the condenser. There's a big area down here called the sump. It usually has a float in it that allows makeup water to come in. Because as evaporation happens, I have to bring in new water to replace the evaporation. Okay, we have slats all over the sides of the tower. Okay, and the water comes down here and falls into the basin. Okay, this area down here, if the water's not treated properly, gets very nasty. Okay, again, this is where I drop the apprentice off with a Tyvek suit, a brush, and some buckets and some cleaning agents, and I pick them up at the end of the day. Okay, and this can get very, very nasty if it's not treated properly. Another type Uses air also. Again, we're pulling air through. Okay? The more air I have across the cooling towers, the better my cooling is. Okay? So again, now the cooling isn't all that great. Okay, 10-degree temperature difference. Not a lot, but it's enough to pull the heat away from the condenser. Okay? Do I want these things running in the winter?
Yes.
What's going to happen to that water at 20-degree wind chill?
It's going to freeze.
Yeah, we don't run these in the winter. Okay, because of the water. No matter how much antifreeze I put in these things, these don't run in the winter.
Do HVAC technicians repair these water towers? Is that our responsibility to fix them?
Oh, yeah, that's your responsibility. Normally, there's a third-party contractor that specifically, they're a mechanical contractor, an HVAC contractor, but they specialize in these things, okay? Now, in terms of the water treatment, okay, normally there's a company that comes in like every other month or sometimes every quarter and tests the water and recommends the changes to the chemicals and stuff like that. But these are the responsibility of the HVAC company. They're part of the system. Fans are used to aid the tower and speed up the cooling. The fans are controlled by the water temperature. The ability of the tower to cool is based on the outdoor wet bulb and humidity. Water has to be able to evaporate. That's a key. The more humid the climate, the larger the cooling tower has to be to get the water to evaporate. I have to have greater evaporation capability. Be careful. Okay, so like up in your part of the country, okay, your cooling towers can be slightly smaller than what I see down in my area for the same load because I'm in a much more humid environment. Okay, we still have to be able to evaporate water. Okay, the larger the cooling tower, the more humid the environment. Again, water towers, just a different picture where we have more slats, we have more bevels. The whole idea is to get that water to agitate and fall down through the slats as we're blowing air through it. So in all of these systems, the water and the air mix. Okay? Water and the air mix, which means any contaminants, pollen, or anything in the air ends up in this water. Okay, evaporative cooling towers. Okay, that's the one that I showed you, the first one. They look like water towers, but the difference is the condenser tubes are in the tower. Okay, all it does is recirculate. Okay, so the condenser tubes are in the tower, so we don't pipe water down through the building. We pipe refrigerant. You don't see these that often. Okay. When the water hits the tubes, it evaporates and cools the refrigerant inside the condenser tubes. Fans are sometimes added to speed and aid the process. The fans are controlled by the head pressure. Anytime you see head pressure, it's the high side of the system. Water is used in the water towers and evaporative condensers that can cause scaling and corrosion. Scale is caused by the mineral concentration that increases as the water evaporates. As I evaporate off the water, I get scale buildup. Okay? Have to bring in fresh water. Have to treat the water properly. The pH levels also changes as the water evaporates. We can use we have automated sensing systems that can check the pH levels. Okay, conductivity. How much the water conducts electricity or electrical current is how we do this in an automated fashion. It can measure the scaling potential and the pH levels. Chemicals are added to adjust the pH levels. We also allow some water to run through the system. We dump some water during operation, so we constantly have some fresh water coming in by the makeup water float and valve. This makeup water flushes out some of the water and minerals. This constant flushing aids in maintaining low mineral concentrations. Okay, now I have one additional picture that I want to show you. This is called a microchannel condenser. This is something relatively new. Okay, you've got to watch out for these things. Microchannel condensers. They have a ton of surface area, ton of little tubes in them. Microchannel. They're very, very small tubes. They're sort of, they're really small. If one of these gets a leak, or if a customer sticks a lawnmower blade through it, or a weed whacker, or something happens to these, you cannot repair these. They cannot be field repaired. Okay? They're used in very high efficiency equipment, but I'm starting to see them come out in a lot of our units, the high efficiency, the very expensive units. Does anybody have any questions on what I covered today?
So if that was to get, say, hit with a stone from a lawnmower or something, and one of those lines in that micro channel was to break, all the coolant would leak out of the system.
Yes. And you cannot braze it. These are most often aluminum. So it's a matter of, this is a condenser coil replacement.
And I'm assuming because they're new, they're expensive.
Oh yeah. Yeah, it goes back to the old story. You get what you pay for. Okay, folks. Any questions on anything I went over today? There's more to this presentation, but it's all about subcooling. I want to cover that when we're fresh tomorrow. Okay. There are some assignments on today's. Module. Please do not lose track of them. Okay. And that's basically all I have for today. I will see everybody tomorrow.